This is the electrical power distribution network for the MV overhead line. When the fault detector is not installed and fault will occur here, then the line person goes to check feeder to feeder and close the switch gear at feeder to feeder. So this will take a few hours and reduce the lifespan of the switch gear. But when the fault detector installed in the network and fault or face-to-face faults occur, then the LED will blink in the network as shown. Here the LED will blink and line person only follows the blink part of the fault detectors, and it will detect the fault in very short time.
This is the block diagram of our project. Here, the MSP430G2553 controller is the heart of our system, provided by the Texas Instruments. Here we use lithium thionyl chloride battery 3.6 voltage. In this system, current transformer sends the current from the line and give the according voltage across the load resistor. Here we use the capacitor for filter the signal from the current transformer. It is fed to level shifter block. The level shifter block shifts the signal at VCC by 2 level. The signal give to comparator and microcontroller. It will convert the square wave for trigger the controller from power saving mode. The DIP switches is used to set the maximum threshold value of the current and time delay for the flashing of the LED. Here the flashing LED is used to detect the fault, so lineman can easily detect the fault. Reset switch is used to reset the circuit. Here we use read relay so user can easily reset and stop the flashing by magnetic stick and no need to climb up on the line for reset.
This is the current sensor placed nearer to the MV overhead line, and it sends alternative magnetic field produced by the MV overhead line. These current transformers gives the output voltage proportional current passing through the MV overhead line. This is the laboratory demonstration circuit of our project. Here we use TPS7333Q for voltage regulation. It is the member of family of micro power low dropout voltage regulators from Texas Instruments. It gives constant 3.3 volt at the output. The input from the transformer after the filtering through the capacitor reach the op-amp, which act as a level shifter. Here we use OPA2379 low voltage operational amplifier from Texas Instruments. It has designed for low battery power application and it has single supply operation with rail-to-rail capability. The output of the level shifter goes to comparator and microcontroller. Here we use TLV3402 family of nano power comparator from Texas Instruments. It makes device ideal for battery power application. It also have reverse battery protection. The switches we used to set the time delay for blinking the LED and set the maximum value of the current. If the current will exceed from the set maximum threshold value, the microcontroller sends signal to LED for detecting the fault. Here we use MSP430 ultra low power mixed signal microcontroller from Texas Instruments. It have 5 power saving mode and ultra fast wake up from standby mode in less than 1 microsecond. It is used to increase the life of battery. So it is the microcontroller it very useful for long life operation. This is read relay. It is used to provide magnetic reset facility. When user detect fault and want to reset, they can easily reset by the magnetic switch through the read relay. This is the laboratory demo of our project. In practical, we use lithium thionyl chloride battery and give input from the transformer here. Here we give input from the function generator behalf of transformer. Here we can see The output of the level shifter. The level shifter shifts our input to VCC by 2 level, as we can see at the CRO. The shifted signal is going to the comparator stack. Here we see the behavior output of the comparator at the CRO. The square wave is coming at the output of the comparator. The output from the level shifter and comparator block goes to microcontroller. Here we use DIP switches for set the time delay for the blinking of LED and set the threshold value. Here the status of the switch is 0000. So the blinking pulse is 4 and value of this is 300 millivolt. So here from the function generator I change the value of the voltage. If I change and create a fault, then LED pulse will be blink 4 times, as we can see. And if I change the status of the switch from 0000 to 1111 for the demonstration and reset my circuit, we can see that the threshold value is also changed and the blinking pulse duration is also changed. Create a fault. 3, 4, 5, 6, 7, 8. So by changing the switch status, the LED pulse blinking time is also changed, as we can see from 4 to 8. We are now on the practical designing of our project. We would like to say thanks to our mentor, Professor Ravi Bhutani, lab assistant Mr. Bhimani sir. And we also like to say thanks our HOD Patel sir for practical demonstration and verify our project. The Paschim Gujarat વીજ Company Limited Porbandar give us the permission to test our product. We would like to say thanks to our college Marwadi Education Foundation and Texas Instrument for giving us this opportunity to verify our idea and test. Thank you.